Chapter 29 Electromagnetic Induction and Faraday's Law. HW number 9. Chapter 28, Lead.18, Lead. 31, Lead.40. Chapter 29, Lead.3, Lead. 30, Lead. 48 due Wednesday, April 22nd. Chapter 29 Opener. One of the great laws of physics is Faraday's law of induction, which says that a changing magnetic flux produces an induced EMF. This photo shows a bar magnet moving inside a coil of wire, and the galvanometer registers an induced current. This phenomenon of electromagnetic induction is the basis for many practical devices, including generators, alternators, transformers, tape recording, and computer memory. 29-2 Faraday's law of induction, Lenz's law. Conceptual example 29-1, determining flux. A square loop of wire encloses area A1. A uniform magnetic field B perpendicular to the loop extends over the area A2. What is the magnetic flux through the loop A1? Solution: assuming the field is 0 outside A2. The flux is BA2. 29-2 Faraday's law of induction, Lenz's law. Faraday's law of induction. The EMF induced in a circuit is equal to the rate of change of magnetic flux through the circuit. Or 29-2 Faraday's law of induction, Lenz's law. Example 29-2, a loop of wire in a magnetic field. A square loop of wire of side L equals 5.0 centimeters is in a uniform magnetic field B equals 0.16 T. What is the magnetic flux in the loop, A, when B is perpendicular to the face of the loop, and B, when B is at an angle of 30 to the area A of the loop? C. What is the magnitude of the average current in the loop if it has a resistance of 0.012 ohms and it is rotated from position B to position A in 0.14 s? Solution: A. The flux is BA equals 4.0 by 10 to 4 Webers. B. The flux is BA cos θ2 equals 3.5 by 10 to 4 Webers. C. The EMF is delta phi B slash delta T equals 3.6 by 10 to 4 V, then I equals EMF slash R equals 30 milliamperes. 29-2 Faraday's law of induction, Lenz's law. The minus sign gives the direction of the induced EMF. A current produced by an induced EMF moves in a direction so that the magnetic field it produces tends to restore the changed field. Or, an induced EMF is always in a direction that opposes the original change in flux that caused it. This is Lenz's law. 29-2 Faraday's law of induction, Lenz's law. Magnetic flux will change if the area of the loop changes. Figure 29-6. A current can be induced by changing the area of the coil, even though B doesn't change. Here the area is reduced by pulling on its sides. The flux through the coil is reduced as we go from A to B. Here the brief induced current acts in the direction shown so as to try to maintain the original flux, phi equals BA, by producing its own magnetic field into the page. That is, as the area A decreases, the current acts to increase B in the original, inward, direction. 29-2 Faraday's law of induction, Lenz's law. Magnetic flux will change if the angle between the loop and the field changes. Figure 29-7. A current can be induced by rotating a coil in a magnetic field. The flux through the coil changes from A to B, because theta, in equation 29-1a, phi equals BA cos θ, went from 0 degrees, cos θ2 equals 1, to 90 degrees, cos θ2 equals 0. 29-2 Faraday's law of induction, Lenz's law. Problem solving, Lenz's law. determine whether the magnetic flux is increasing, decreasing, or unchanged. The magnetic field due to the induced current points in the opposite direction to the original field if the flux is increasing, in the same direction if it is decreasing, and is zero if the flux is not changing. Use the right-hand rule to determine the direction of the current. Remember that the external field and the field due to the induced current are different. 29-2 Faraday's law of induction, Lenz's law. Example 29-5, pulling a coil from a magnetic field. A 100-loop square coil of wire, with side L equals 5.00 cm and total resistance 100 ohms, is positioned perpendicular to a uniform 0.600 T magnetic field. It is quickly pulled from the field at constant speed, moving perpendicular to B, to a region where B drops abruptly to 0. At T equals 0, the right edge of the coil is at the edge of the field. It takes 0.100 s for the whole coil to reach the field-free region. Find, A, the rate of change in flux through the coil, and, B, the infant current induced. C, how much energy is dissipated in the coil. D, what was the average force required, fixed? Solution, A. The flux goes from BA to 0 in 0.100 s, so phi B/T equals BA/T equals minus 1.50 by 10⁻²⁵ Webers per second. B. The inf is n phi B/dt equals 1.50 V. The current is inf/R equals 15.0 milliamperes. C. E equals PT equals I2 RT equals 2.25 by 10⁻³ D. F equals WD equals 0.0450 N. 29-3 EMF induced in a moving conductor. This image shows another way the magnetic flux can change. Figure 2912a. A conducting rod is moved to the right on a U-shaped conductor in a uniform magnetic field B that points out of the page. The induced current is clockwise. 29-3 EMF induced in a moving conductor. The induced EMF has magnitude. This equation is valid as long as B and V are mutually perpendicular. If not, it is true for their perpendicular components. 29-3 EMF induced in a moving conductor. The induced current is in a direction that tends to slow the moving bar. It will take an external force to keep it moving. Figure 2912b. Upward force on an electron in the metal rod, moving to the right, due to B pointing out of the page. 29.3 Motional EMF 3. Electric force Phi balances FB. Moving rod in B field, greater than electrons experience FB. 2. Electrons move in the direction of FB creating a charge separation and E field. 3. Electric force Phi balances FB. Equilibrium. B. Phi plus L E V dash FB dash. 13. Question. A conductor is moving downward in a magnetic field pointing into the page. Which sketch below shows the correct motional EMF and current directions? A, B, C, D, V, B, V, B, V, B, V, B, I, EMF, 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 EMF.